So we had gotten a little bit behind, and it's my fault. And so I fixed Canvas to reflect what really happened. So we had 2 days of gain bandwidth, and really it's 2 days worth of content. And so to orient you, a lot of what we did, right, these were probably the original notes, and then maybe why op amps ring. But now here's how to do a Bodie plot with op amps, which is like homework 1. Yeah, there's a video of it as well that I didn't mean to click on. Oops. And then there was the class lecture where we kind of went over that, right? That's just the video from. Then there's modeling the gain bandwidth of op amps with more than one pole, and also buried in there is whether an op amp will be over, under, or critically damped. So that's like it's either problems 4, 5, and 6 or 3, 5, and 4. But the last 3 problems on the homework. And then here's the video lecture from last time. So if you're wondering if things change, that's I just made it reflect what we really did. All right. Now today, yeah, we'll start with the Fourier series, right? And so we have an introduction, finding the DC average, some notes and examples. There's the homework. I put the chapter 5 from the book last because it's all the information it's accurate, but I don't know if we need it all, right? Because what we hope to get out of this course is to calculate line spectra, and then there's even, and the thing is there's the Fourier coefficients or the Fourier spectra, and then there's the Fourier transform, okay, which is really a subset of the Laplace transform. So today we'll get through as much as we can of this. Then when we come back from break, we'll finish up Fourier. All right. Now, I just want to spend a brief moment talking about, just what it is we're doing. And you kind of have to forgive me because sometimes I will talk about the Fourier series and transform, and I'll forget that really they're 2 different things, and I get talking so fast. All right. But the Fourier series is just, an infinite sum of cosines and sine waves, with different amplitudes. And, well, there's more than one way to represent it. If you use cosines and sines, the phase is always 0. But if you just combine these into one term, then they have a phase as well. All right. So, I think the book has a great, take the Pink Floyd cover, and yeah, I am not drawing these in the proper order color spectrum, okay? So you take a certain color of light and a prism breaks it off into different frequencies, right? So frequencies of light, right, are they're sine omega t. It's just omega happens to be the frequency of whatever light you're looking at, right? And in physics 52, yeah, you spend a lot of times not talking about it that way, but by using rays. The frequency is so high that it can act, you can sometimes approximate it like a ray of light, right? So each one of these is a different frequency. Well, if we take any signal, any periodic signal, and I'm just going to kind of draw some random thing, right? And now let's just, so this is an arbitrary signal. But if I just repeat it again and again and again, I can make it periodic, right? So if this song represents, I mean, if this data represents the song, oh, I don't know. Fight for your right to party, right? This is the whole song. This is several minutes long, right? And then I repeat it. I can do a Fourier series on it and turn that song into an infinite sum of sines and cosines. I'm not getting a lot of recognition on that song, so yeah, that's I'm just going to let that go. All right. Now, there's certain signals that we deal with, right? Like maybe DC or pulse or sine, triangle, classic signals. And yeah, we're going to break these up into sines and cosines. Now, that's a somewhat similar where we would take any signal and try to break it up into steps and ramps and things like that. But the big difference is they repeat for minus infinity time to plus infinity time. All right. That's and it's the and the other term is ever lasting. Okay. So I know I looks like it has a start and an end, but with the Fourier series, the whole point is that it's everlasting. Where if we break this up into step functions, right, it's ut minus 1, and we get one pulse. But then unless I start adding another ut delayed, I won't get any pulses. I have to keep repeating this over and over and over. And yeah, another thing is that when we talk about Laplace, right, even if I have a sine wave, before t equals 0, right, it's 0. So Laplace is like this, 0 and then you have a sine wave, 0 and then you have a pulse, 0 and then you have triangle waves. And then they, in a sense, and then they stop, right? Here, no, this is going on for infinity either way, everlasting. Now, nothing is everlasting, but usually with our electronics, after a second, it's effectively been on forever, right? So if you have a time constant of a circuit that's a millisecond and it's been on for a second, well, that's 1,000 periods it's been through, right? You might as well be infinity, right? The whole thing with infinity is, can we have infinity? No, but we can see it from here. All right. Now the Fourier transform, and that is an actual transform. And that's not really what today's about. So if I'm getting this a little bit wrong, right, I'm not going to sweat it. which looks awfully like the Laplace transform. And the difference is right here, S. Here, right, it's j omega. That is what's being transformed, and the function we get is a function of j omega, this imaginary number alone. Okay, here, S has a real and an imaginary part. So we have our real and imaginary axis, where this, we just have a number line with j on it. Now here's just the really interesting part to me, is that if I take the Laplace transform something and I calculate the magnitude and phase along this axis, okay, I've just done the Fourier transform of it. And I thought that was pretty cool. It took me a long time to figure that out. Maybe you guys saw it right away. So we're gonna, when we are going to, so we've already kind of done this, but later on we're gonna go back to the Fourier transform when we're going to do filters. All our filters have been, excuse me, so far, we've had one pole, we've had two poles that are real, we've had two poles on the same spot, but we really haven't, we've touched on it in our DF2 analysis, but if I have two poles that are imaginary, right, even though they're off here in the S-plane because it's got a real and an imaginary part, and the Fourier transform is only this, when we find out the response along the j omega axis, right, that's the Bode plot. And we're going to talk about making filters by just putting poles and zeros around and then seeing what we get. Okay, that's after the midterm. All right. And just as a heads up, why are we kind of breaking with the op amp part right now and almost just like screeching and going into Fourier transform? Well, the project is a pulse width modulated deck. All right, where the period is fixed, but you can control the output of data by how long it stays high. Okay? So there's information, right? So in this blue line, it's staying high for a greater percentage. That's going to represent a higher number. When it's at a lower number, when it's staying high less, it's going to represent a lower number. And so this kind of pulse width, we put into a low pass filter, which is actually averaging this. And so if I'm taking the average of a signal with a small duty cycle, I'm going to get a number down here, or I'm going to change colors, right? I'm going to get a number here. If I'm taking the average of something 50%, I'm going to be up here. And if I'm a bit higher, I'm going to be here. And so a low pass filter can, you can get analog values out of it. The trick is it can get tricky, and to analyze this properly, we need to convert these pulses into a sum of sines and cosines to better analyze it. All right. So if I don't start it now, by the time of the final project, you won't know why we're doing what we're doing. But really, ultimately you get these discrete magnitudes, right? If you have a DC average, you have a number. Then at omega naught, you can have another magnitude. So this is a sine wave, and this is just a magnitude. This is 2 omega naught, and maybe it's like this. And this is 4 omega naught, and maybe it's like this. And maybe 6 omega naught, we have another big thing. So here are these, this is the frequency axis. It's linear, right, not log, because we've got the 0. So if I want to get rid of this frequency, all I got to do is draw a box keeping what I want, getting what I want to get rid of, and then letting back in what I want, right? And so this is kind of a notch filter. So by doing that Fourier series, you can find out that frequency information, and then you can filter out what you want. Now, really, just so you know, we're trying to get the DC average out of this. So we are trying to filter this part. We want this, and we're trying to get rid of everything else. Now, yeah, this can never go straight up and down. Some of that first harmonic will always be there. But higher order filters will get rid of more data. So that's like the big picture. Any questions on that? All right. So here's, I want to, rapidly get to calculating these spectrum by hand, right, or mathematically. But here's what I just said mathematically. Okay. Oh, anyway. We take a periodic signal. And like I said, you can turn anything periodic just by repeating it. You could take the life of the universe up till now and repeat it, and that would be a signal that you could do the Fourier analysis on. So there's more than one way to show it, where you have an A constant, and this would be the DC part, and then an infinite sum of cosines and sines. Now there's another way to show it where you have a DC thing, and then you just have cosines, right? And the way you make up for the fact that you don't have sine and cosine is you have a phase, all right? Then there is the exponential method, where you can actually show the negative frequency components, which, yeah, can be a little mind-blowing, so I'm just going to leave it for now. The reason why the Bode plot, we always use positive frequency, is because Bode means log of frequency, so you can't have a negative or zero frequency. But if you look at the Laplace transform, the S-plane has positive and real parts and positive and real imaginary parts. The imaginary parts are frequency. And so this thing can show the fact that there is this negative frequency domain. We usually kind of ignore it, but sometimes you can't. Omega naught, that is the fundamental angular frequency. So once you find the period of the waveform, right, you can calculate omega naught, and everything will be, you'll have a DC part, maybe, then you'll have a fundamental frequency, and then you'll have, 2 times the fundamental frequency, 3, 4, 5. Now sometimes it skips, but and then the fundamental frequency is when n equals 1. So that's really the frequency that you look and get just by looking at the waveform. That is the fundamental frequency, right? And then harmonics is just n times that, right? I already mentioned that. Here are the ways to calculate the coefficients. So I have xt, right? That's my periodic signal, and I want to break it up into an infinite sine and cosine representation. Well, the first part is really just the average, right? 1 over t from 0, integrated from 0 to t naught of the signal. That's the definition of average, right? It's now, if I squared this and took the square root of it, oh, that's RMS, right? This is just average. You find the AN constants by multiplying your signal times cosine and then integrating. You take your BN constants by multiplying by sine and then integrating. Now, there's a lot of rules about even and odd functions and can make your life a little bit easier, but when you're first learning it and calculating it, all of a sudden these rules just pop out, like, sine of the sine at half the period equals the sine at the period equals the sine at the beginning of the period. And then things cancel out because of that. I don't think we need to go into that right now. So finding AN and A naught and omega naught. So remember, right, we have A naught plus AN, I think it's cosine plus BN sine right? That cosine and sine are n omega naught t. So finding omega naught and finding A naught is actually almost the most important part, right? Once you do that, and you can do it by eye. Now, I spoke to Professor Morelos, who uses this a lot in 160, and you could think of it as like, he's my customer. Did I prepare you for 160? And he said these two skills are super important. So I'm going to spend some time on it. And in fact, yes, there's homework on it. So like I said, we can take any periodic signal and break it up into an infinite series. Now, this isn't a homework assignment, but I like to take something simple like a DC signal and see what would the Fourier transform of a DC signal would be, right? And you're thinking it's DC, it never changes. The Fourier series will be like nothing, right? But let's apply it. Now, like I said before, this is an LT spice. It starts at 0 and goes to 5. But for the Fourier series thing, this goes to negative infinity and this goes on forever. All right. So what's the period? Right? Is it half a second? Is it 5? And then I'm going to repeat it. And yeah, this takes a little bit of an imagination. But if this goes on forever and it never changes, and this goes on forever and never changes, well, the period is infinite, right? So then omega naught is 0. All right. Now, we don't actually need that right off the bat. I take A0, right? 1 divided by T naught, integrate from 0 to T naught, 1 volt. All right? That's the integration. And then it turns out, without having to worry about what T naught is, I just get 1 because the T naughts cancel out. So the average of a 1 volt DC signal is 1 volt. And it made me think, I knew that. But I like to, when I'm learning something new, I like to tie it to something simple that I can't possibly forget, like DCs don't change, right? Now, right now we're saying, what is the period? What is A naught for this signal? The period is infinite, omega naught is 0, and A naught is 1. But I thought, why not find the other coefficients? So you just say, oh, AN, 2 divided by T naught, 0 to T naught, 1, that's our function, times cosine n omega t. Integrate it. And then what you'll find is that the average of this, right, because there's no DC offset here, so the average of a sine or a cosine in even periods, right, is 0. And it's going from 0 to the period. So you know intuitively it'll be 0. But then not only that, omega naught is 0. So whatever value in here, right, is going to be 0. And 0 minus 0 is 0. All right. Now, I said we can break up any signal into an infinite sums of cosines and sine waves. Well, what if I put in a sine wave? I should get a sine wave. Well, let's look at it. Let's look at the average by I. It goes up to 1. It goes down to minus 1. You know, that looks like it's going to average at 0. So A naught is going to be 0. Frequency, well, the period is 1 second. That's 1 hertz. So omega naught is 2 pi over 1 second, or 2 pi radians per second. Okay. So I found omega naught. I found A naught. And that would be enough for that homework question 1. But it's a sine wave. We can clearly see it's a sine wave. And so there's nothing else there. So I can just say all the ANs are 0, right? And then the BNs are, since there's only one sine wave and it's all composed of B1, anything higher than B1 is 0 as well. But what is the Fourier expansion of this? Xt equals B1 sine omega naught t. And yeah, maybe you guys don't like the phrase when professors say this, by inspection. But I have other notes where I actually derive that out. But, I think there's something to be said for looking at things by eye. Periodic signal 2. All right, I see a sine wave. Looks very close to a sine wave. The period's half a second. Okay, so now I'm getting 2 hertz or 4 pi radians per second. But now, oh, wait a second. It's starting at 0 and going at 1. And because it's a sine wave, right, I know that if I draw a line down 0.5, it's going to be even, right? You could have anyway, a sine wave, it's just easy to say that the average is 0.5, right? Just for looking at it. Now, there's a sine wave. It's captured by this constant here. So all the ANs have to, greater than 0 have to be 0. And what is the Fourier expansion? A naught, which is the half, plus B1 sine omega t, which is that. And really, so just not even doing any integration, just for looking at it, we've done that. And the thing is guess what? Well, oh no, I'm going to tell you later. You're going to have to wait. Now, let's do our next periodic signal. It's a square wave. The period of this square wave is 2 milliseconds, so omega naught is 1 kilopi radians per second. I'm looking at it by eye. It's going up to 500 and down to minus 500. Now, if this is on a scope, you can click average, and it'll tell you what it is, right? So, and the scopes are smart enough to figure out what the period is. Although, or maybe it, because the thing is if I simulate this up to here, LT Spice will give the average as, it won't give a half because it wasn't the same amount of time up as the same amount of time down. So yeah, in LT Spice, you can click control and it'll give you the average, but you got to make sure you did it in even numbers of periods or you'll get a funny answer. Okay. Well, so we have our omega naught 1 kiloradians per second. We're able to easily see the period. We can easily see that A naught is 0 because it's averaging out, right? And yeah, if in fact it was a little, if it was on longer than it was off, right? There A naught would not be 0. So even though it's going plus 500 and minus 500, if the duty cycle wasn't split exactly between the two, A naught would not be 0. Now, even though we found our omega naught, we found our A naught for a 50% duty cycle signal, let's just see what what kind of Fourier spectrum we're looking at. And remember, I said I can make any periodic signal into a sum of cosines and sines. Well, omega naught is already given. So I could try a cosine or I could try a sine. And I thought a sine would fit better. All right, so here's a sine wave. And so this sine wave is an approximation of the square wave. Now, of course, right, there's this error in here where it's not the same, right? It's not a perfect representation. You might even say it's a terrible representation. But A naught equals 0 and B1 or B1 equals 0.5, and so you get 0.5 sine omega naught t, right? So that's my Fourier series expansion up to n equals 1, right? So now to more fully do that, you would start adding more sine waves to fully represent, and it would get closer and closer, right? There'd always be some ripple, and that's a conversation for another day. But yep, just for looking at a square wave, right, we were able to take the average and find A naught without calculus or calculus in our head, and then put in one sine wave to show that, yeah, we've got the first coefficient. Periodic signal 4. It's a square wave. It's 50% duty cycle, right? The period is 2 milliseconds, but it goes from 0 to 1. So in fact, there is a DC average. And yeah, what's the area of this averaged with the area of this? Well, the area, it comes out to be a half, right? When you take into account the period. So A naught is just a half. And I can put in one sine wave, right? So if I add a half to a half times a sine wave at a kiloradian times t, I get this blue line, right, as an estimate. And I would just need more terms to represent that square wave. But here's the thing, that fundamental frequency is the most important frequency to our project. All right. So this is 0. Oops. This is omega naught. I'll just draw it. So omega naught is 0.5. Right? That 0.5 is the magnitude. So that's a sine wave at omega naught with an amplitude of 0.5. And the DC average also is 0.5. I think I want a different color. Okay. So now, when I want to do my low pass filter to get rid of this, I want the average. The pulse width modulated filter is trying to get the average and get rid of all the other information. So I would just try to draw. Now this is a linear scale, so it's going to look like this. And you see the negative frequency. It looks like a bell curve, not what I drew. Now, yeah, a low pass filter on a log scale on a Bode plot, yeah, it looks more like that. But this is really what the shape looks like on a linear scale. All right. I get rid of the sine wave and I get back my average. Okay. Here we go. This one's a little bit harder to see, I think. But the way it's arranged, that it's a square wave and it's rising for the whole period. It spends half its time below 0, half its time above. The slope doesn't change. This will actually average out to 0, so A naught is 0. The frequency, the period is 1, so omega naught is 2 kilopi radians per second. All right. Now, maybe with more experience, I could guess the first one. So will I have, what will I have? Will I have a sine wave as the fundamental? Will it be a cosine, which starts up here? Or will it be a sine wave with a delayed phase that starts low and comes up high? I thought that was like too much for this particular bit. All right. But then we have another gotcha. Here's a square wave, a triangular wave, but you can see that it's on for some time and it's off for some time. It's almost like the pulse width modulated, right? Where it was on and then off. Here it's rising and then it's off. So the period is still 2 in this example, but there's 2 areas or 2 regions, one where it's 0 and one where it's not 0. So all I got to do is find the average area of this, or the average of this, plus the average of this, which turns out to be 0, divide it by 2, and then I'll get what I'm looking for. So here it is in equation form. Okay. Does anybody have any questions so far? All right, so we're missing like 10 people. I know it's spring break. It is recorded, but you know, if your friends ask for the notes, I guess I would just give it to them. But I mean, that was a lot of information. You sure there's no questions? All right, so I'm just going to repeat what you said. So I'm saying, hey, is there any questions? Everybody says they're an expert because they had 112. No, that wasn't exactly what was said, but yeah, 110 and one. I see you. Let me finish. And so 110 and 112 are very similar, and they kind of have an overlap. But when I coordinated with Professor Santa Cruz, um, he said I kind of had to do this part, right? And so he might have jumped right in there. And yeah, the Fourier Spectra lends itself more to, I would say, DSP and leads right into it. But not everybody takes 112 with 110 and 110 lab. And, you know, maybe it's just like he has his way and I have my kind of different approach, and maybe between the two. So it's okay. There's no questions. Alexandra, you had a question? Okay. Yeah. My slides tend to be, the question is, it seems kind of dense. My brain is full. I have to go back and digest this before I even know what to ask. Yeah, it's true. These particular notes didn't exist, but I kind of, and I'm not blaming anybody or making a scene, but even if you just read the book lightly, you'll kind of like you're prepping yourself, um, because that's kind of how things are supposed to be taught. You read up a little bit, and then you can follow the conversation. But that's the thing. You might read that chapter and be totally lost, but that's still better than coming in. Like if you don't read the chapter before you come in, you're like totally lost squared. Again, not thank you for making your comment. I'm not trying to. Does somebody else? All right, that's the question, right? What's on the exam? Um, these slides right here were question one, right? On the homework. On the exam, yeah, usually I have a question on, I'll make up some signal and you tell me A naught and omega naught. So these were like the square wave and the this triangle wave. Yeah, that's more a exam level question. Other things that I haven't gone over are, I'll plot out some spectrum in Python, right? And then I'll plot out some function, and then I'll mention some functions, and you have to play the matching game. Um, I think at that point, I should just go over the notes on how to do that. That's it's a homework set. I have notes on that. It's hard to draw, so I'll just show it to you a little bit later is what I'm trying to say. Like, but yeah, but just because you don't have to calculate the whole Fourier series on an exam doesn't mean that's not like a skill that you would need to do. But in like exams to me are like job interviews. So like what can you do in your head, right? Well, A naught and omega naught, and hey, can I squeeze a sine wave in there or not? Right? Or maybe it's a cosine I should squeeze in there. All right. But some problems, yeah, you can't ask them on an exam because it'd be one question and you'd need a reference library to answer, right? So homework is more than just exam prep. Um, some of them are life prep. Uh, does anybody want to chat me a question before we move on, or was that everybody? Okay. So yeah, here's homework 9. Find the DC average and period. That's effectively finding omega naught and A naught, right? Then here's like a higher level question. There's 3 ways to represent this. Just describe the benefits of each ways. It's in the book. It's more of a researchy thing, right? I kind the book talks about this as well because yeah, if I'm going to teach something, I really, really don't want to waste your time. And so I proved to myself why we have to teach Fourier and just can't get away with Laplace. Because it's funny, Fourier is just, it's all right, it's sines and cosines, but the Fourier transform is just a subset of the Laplace. All right. So, yeah, you really want to know when to use what. And then, yeah, here's one where you have the answer, and I just want you need to go and find it. Then you need to plot out a few, right? But then the question that you just, like I said, what would be exam questions? Here's 6 waveforms, right? Sine 2 pi 50, half sine 2 pi 80. All right, so we have a sine wave at 50 hertz and a sine wave at 80 hertz, but its amplitude is a half. All right, ooh, darn it. So then what I've done is just plotted these out in Python. All right, can it be this one? Well, this is a half, so the constant is a half, and there's a sine wave centered at 80, but there's only one, so it can't be that one. Okay. Here's another one, but it's centered at 50, and its magnitude is 1, so that can't be it. This one's at 50, and this one's at 80. This constant is at 1. This scalar is at a half. Well, there you go. That was number 1. Oh, and then I already did 2 and 3 just by scrolling through. And then, wait, is this the same one? Uh-oh. 2, well, I guess I found an error. Waveform 4 looks just like waveform 1. Oh, I'm sorry. I can't. Oh, thank you. No, I guess I didn't make a mistake. what happens is that when you multiply sine waves together, you actually change the frequency. All right, so that's like a little hint. And then remember our full wave rectifier, right? You had a half wave rectifier, and then when you did a full wave rectifier, the period doubled, right? That's what's going on here. So if I have a sine wave, right, the frequency doubles, not the period. I take the absolute value of that, right? Now it's repeated every t divided by 2, or the frequency doubled. So if I take the absolute value of a sine wave, of a 60 hertz sine wave, I should get something with 120 hertz, at least at one frequency. Okay? And yeah, multiplying two sine waves at different frequencies, you don't really get, because of this kind of effect, you're not exactly getting the same omega naught that you got before. Bless you. Well, the drawing might not be that great, but let's say we have a microcontroller that puts out 0 to 5 volts. Okay, so what's the average of that at 50%? 2.5. I can put a sine wave in there, right? And I'm pretty sure I'm going to have sine waves and no cosines. So sines, but no cosines. So I kind of, because you can really get into it and almost forget what you're doing, right? Because the math takes so long. Now, so xt equals a 50% duty cycle, 0 to 5. Well, this can be broken up into two regions, right? And I was listening to my videos, and I think I say right a lot, and I'm sorry. Okay. The fancy way, we did it by eye, but there's our A naught. Sometimes I need help remembering. So we already found A naught. Let's find A1. So A ends are 2 divided by T naught integral 0 to T naught xt cosine and I'm putting a 1 here, or no, I'm going to put n rather than just 1. 2 pi T naught T dt, right? And that has 2 regions. Now I want to take a shortcut. Is that we're integrating cosine, all right? And we're not multiplying it by anything else. So that means we're going to get sine, right? And 2 pi T. Oh, sure, we're going to get this other parts here, and things go minus and they go negative. But if n equals 1, we get sine 2 pi t naught divided by 2, because I'm substituting t naught divided by 2 here, right? Minus sine 2 pi 0 divided by t naught. And this is always 0. The t naughts cancel. I get sine 2 pi divided by 2, right? Which is the half cycle of a sine wave. And that's always 0. Now, let me bring back the n that I had ignored. Well, if n is 1, right, it's still half the period. If it's 3, right, I get 6. I guess what I'm saying is no matter what, right, you're going to be here, here, or here as this repeats, as n gets bigger and bigger and bigger. So it's always going to be 0. So if we recall, the Fourier transform is made up of cosines and sines. The cosine part, right, the A naught is the DC part. Okay, but then the rest of them are cosines. And we had observed that it didn't really look like a cosine was there anyway. And I kind of made a prediction that I'd made a prediction that it wasn't there. I mean, all those constants are 0. And without having to go through the whole thing, okay. And then, yeah, to set up Bn, we're going to get something like that. Now we're running a little bit late. I'm sorry. I was redoing the. This was what it was instead of 0 to 5. And so here, so these notes are online. So rather than my handwritten notes, you can see that this averages to 1. On the previous example, we averaged it to 2.5. Then our ANs, right, here's the formal derivation, right? And that we can see that whatever n is, this is always going to evaluate to 0. Then for our bn, all right, 2 sine, we integrate that, we get minus 4 divided by n omega naught t naught, right? We evaluate it here. And yeah, we get minus 1, which doesn't cancel. We get minus 2, which then turns it positive. And when we work out all the algebra, we get 4 divided by n pi, if n is odd. Now, if n is even, it turns out that, no, you're right back where you started from. So really, you would have a Fourier spectrum. You'd have your average here at 0. You have your fundamental frequency at omega 1, right? It skips omega 2, and then you have something at omega 3. It skips omega 4. You have something at omega 5. All right. And you can see that it goes down. So in this case, 4 divided by 1. So it's really kind of 4 divided by pi. All right. So it's a little bit less than 1. Then it's 4 divided by 3 divided by pi. 4 divided by 5 divided by pi. And so it gets progressively smaller. Now, so we've talked a lot about low-pass filters, right? This was a simple one, right? And then we've talked a lot about gain bandwidth, right? And here's the thing. I did it in a video, but this circuit by itself can be underdamped in some cases. All right. And so I have a low pass filter here, right? And then it can come down. But then if this is underdamped, the Bode plot can actually shoot up on me. All right. And if I put in a step response, oh, that's low pass, but this can actually kind of ring on me. All right. Which is a problem. Or the fact that, you know, we've got this behavior. And you might say, well, you know, I have a low pass filter and everything should be fine. This is just a square wave. It's a kilohertz square wave. So I have a kilohertz over here. Out here, you know, it's 10 megahertz. Who cares, right? But now we know that this pulse, right, it has omega naught at, well, I'm going to call it F naught, right, at 1 kilohertz. F1, F1 is 1 kilohertz. F3 is 3. F5 is 5, right? And here's the thing. Even though the magnitudes are going down, it's an infinite series, right? And so when we put in this square wave, whereas before in the past we didn't really care what was going on out there. It's like a high frequency. Or if you're doing a Bode plot at 97, you keep your sine waves well below that. But when you put in a step, right, which is really a very long pulse, you are getting these frequencies, right? And they're infinite whether you like it or not. So if the frequency of my pulse width is here, right, at 1 meg, right, well then the next, if that's the fundamental frequency, the next one is 3 meg, and it's right in my gain bandwidth problem, right, area. This is super high level. Maybe, I just lost you, right? But the big deal, these things make infinite sines and cosines, which then when you're doing your op-amp based circuit, the gain bandwidth senses that and can cause troubles in your circuit. But and just so you know, I'm probably going to mention it in some way or another almost every day until the end of the semester, because it's going to hit you at different times. Okay? But it's so after break we'll do more expansions. All right. Does anybody have a question before you go skiing, or probably working really hard is probably more like it? All right. My online folks, you guys got anything? All right. I'll probably post these notes, the video tomorrow. All right. Take care.